God.
Hi, Kay.
Hi, Sean. How are you?
Good. How are you? Yeah.
Doing pretty good.
Okay. So, do you have some questions for lab 2? No. Yeah.
No, not for lab 2. I'm just finishing up the last couple of questions for that one.
Okay. Good. Yeah. And, only you. Wait. Let me wait. Let me see whether there are another student. Okay. Oh, see so here. Dun, dun. Dun, 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 dun. Okay, let's begin. Actually, today's class is complex but easy. Complex is for we will talk about the Fourier representation. Easy is for actually in this lab 3 we don't need to know much details of Fourier representation. I mean Fourier transformation. We just need to be familiar with this Fourier representation and use some built-in function to show the Fourier representation. So in this class, it's about okay, yeah, if we look into the document and okay, so let me focus on the first example, the part 1, basic Fourier analysis. Since actually here Fourier transforming has many types. Here we just use the DTFT. DTFT means the discrete time Fourier transformation. Since our data is stored in oh my god. Okay. Since our data is stored in our MATLAB, all data is just a discrete form. It's just the discrete form, and oh my god, another. So discrete form, and we can't store any continuous wave in our MATLAB. We usually just sample the. We should for continuous wave. Firstly, we should sample them, and then store the corresponding data like for corresponding data like this. So then we use our computer to process them, and so for the Fourier transform, we should use this discrete time Fourier transformation. So okay, let's focus on our part 1. Part 1 is this example. If you look into going to this example. Here I have defined. Suppose our sampling frequency is 8,000, and we just define a sinusoid function and with the frequency of 200 in this case. So this is a sine function and sine wave with the frequency of 200. And then we can plot its time representation. Let's print plot. Oh my God, wait a moment. 200 is so fast. Okay, let me change it to be as 20 frequency, 20 Hertz frequency. So you can see this is the wave with the frequency of 20. And now if I increase it to, yeah, we have checked this. It's a rapidly changed wave. Yeah, rapidly changed wave. Now we Fourier transform will tell you the distribution, the energy distribution over the Fourier domain. I mean over the frequency domain. So to see this, we can use the built-in function like this. Here, I just use the built-in function FREQZ, and you can see the input variable include x. X is our input signal, and now it's a sine wave, and this the second variable is a constant. In this case, it's a constant. However, for other cases, it may not be a constant. So this is a constant 1, and the third variable is the number of frequency points. And here, so this may, since I didn't talk about the details of Fourier transform, and I think I don't have the confidence of talking about it properly. I think Professor Zhou will cover this very carefully. And here in NAP3, NAP3's goal is to make you be familiar with Fourier representation, so you don't need to worry about the details. So here you can see the third variable is defined as 2 times the length of input signal, and the fourth variable is the sampling rate. Which is also the sampling frequency. So now we can, so the output is H and F. F is corresponding to the frequency index over the frequency domain, and H is the corresponding value, corresponding amplitude. H is amplitude. So now, okay, let's check this. You can see, since the left-hand side is the sine wave with the frequency of 200 Hertz, and in this frequency representation, we can see the energy has been concentrated on a certain frequency. If we check this value like this, Okay, you can see according to this label, and the X is around 200 and the Y is around 500, which means the energy is concentrated on 200 Hertz. Yeah, if I set our frequency to be 2000, you can see now, 2000 Hertz. So this sine wave is rapidly changed with the frequency of 2000 Hertz. Now you can see in the frequency representation, the energy is concentrated on 2000 Hertz. So this is how to use this built-in function to tell the energy distribution over the frequency domain. Now, okay, I think you have been familiar with this. Now let's move on to the second part. Oh yeah, before move second part, let's check this example. This example. This example, you may see, I have, there are four frequency. They are 500, 1000, 2000, 3000, and the single XY is defined as a combination of three sine waves. They are this one with the one of 500 Hertz, and this one with the 2000. Oh, sorry, this one is with 500, and this one is with 2000 Hertz, and this one is with the frequency of 3000 Hertz. And okay, yeah, the second single is similar with the first one, so we don't need to show it. Okay, in this example, I have defined it as in this way, and okay. And this F analysis is a self-defined function, and so this is just an example for this white MATLAB function. So what it's trying to do is just to give us the frequency representation, as I have showed you. Okay. Now we can see, according to this example, we can plot the, yeah, okay. The left-hand side is the sine, is our single wave. You can see if we zoom in, you can see actually this is a complex single, since you can see for this part, it has a very irregular shape, like this way. Yeah, it's very irregular. So, but according to our frequency representation, we can find the energy distribution is very easy, and the energy is concentrated on three different frequency, and they are 500, 200, and 500, 2000, 3000 Hertz. So they are totally corresponding to the defined frequency F1, F3, and F4, and so this is related to the Fourier transform. I think Professor Zhou will cover this, but now you just need to know we can use the we can use the FREQZ to tell the energy distribution over frequency domain. So yeah, so this is very easy. So now let's move on to the part two. Part two, it's a musical analysis. So now here we have a Yankee Doodle, right? Yankee Doodle. So now we just since I'm not I mean I am not familiar with the music knowledge. I'm a fool for music, but I love music, of course. So here, introduce the Yankee example, I wish you read this part. I mean, this introduction part. It's just give you some basic music knowledge. Yeah, the standard frequency associated with 12 notes and range from 220 to 440. And now their frequency 200 Hertz is known as A frequency S. The next A. Okay. Yeah, I assume you have read this one. And now, okay. Then for the Yankee Doodle. For the Yankee Doodle, no, firstly, let's listen to this music first. Dun, 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 dun. Dun, dun, dun. Dun, 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 dun. Dun, dun, dun. Do, 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 do. Did you hear that? Can you give me some feedback?
We heard it.
Okay, okay. Thank you, thank you. So it's the Yankee Doodle, and according to let me ask you some question. According to this this introduction, how many notes do you think it has for the Yankee Doodle? Let's repeat this music again. Please count the notes. Can you give me estimated answer? Yeah.
There are 7 different pitches.
7 different pitches.
Some are played multiple times, but there are 7 pitches.
Okay, 7 pitches. Okay, but yeah, according to the codes, however, 7 pitches. Maybe you're right. I don't know. I'm just a music fool, but oh, okay. Oh, okay.
Like 27, I think is what I counted.
Yeah, I think that's the answer I want to say. Yeah, since if we check the Yankee function here, this is a Yankee function, you can check it on your MATLAB, and you can see this is the music, and it's a combination of 20 notes. Oh, well, no, it's 27, around 27 notes. Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30, 40, 50, 16, 17, 18, 19, 20, 21, 23, 24, 25, 26, 29, 28. Wait a moment. oh, 27. 27, it's 27 notes. And you can see if we check their codes for each note, oh, let me see. Some of them. Oh, you can see, even though there are 27 notes, however, there are some same notes, right? So I think Trevor may be right, since different pitch is corresponding to different note. But if we just count, the note numbers, and there are 27 note, 27 notes. If we just count the number of different notes, maybe there are only 7 different notes. Okay, so for each note, and for each particular note, they have a certain frequency. For example, for the note A, the frequency is 220 hertz. For another note, sorry, so yeah, this is just a note. Okay, for another one, and they have, it will have a different frequency. So, okay. So now this is the Yankee wave file. If you zoom in, you can check. Actually, you can find each note from according to this wave file. However, what we need to do is to analyze the note in the frequency representation. Here, if we check the first note, you can see the first note has the frequency of C. C is defined as 261.63 hertz. So if we check its frequency representation, I think it's let's do the music. You can see for the first note, the energy is concentrated on, let me check. It's concentrated on 261.3. So, this is just another example to show the frequency representation. Yeah, so you can see, since our music is just a wave, and we can use our Fourier transform to tell the music's frequency representation, and to see where the energy is concentrated. So if we want to create some novel music songs, maybe we can use these techniques to help us. Okay, so this is just the example of Yankee, and the second, the part 3. So for part 2's other task, for part 2, you will, okay, let me see. You will also allow us the Yankee Doodle with harmonics, right? I don't know. And you should also deal with the Yankee Doodle with amplitude variations. So for these 2 examples, and you will find the every note, you will find the note will have a different frequency representation. And since we have done some we have processed the loads, so you will find a different energy distribution. Okay, so let's move on to part 3. Part 3, we will deal with the Beethoven. Beethoven. Beethoven's piece and the circus piece. Okay, for the Beethoven's piece, it's very easy to do. You can see Beethoven's piece. Beethoven. Here is Beethoven. And let's load the Beethoven. Here, wait a moment, load it, and then we can show it. Hey, where's my Beethoven? Okay, here is Beethoven. And define the sampling rate if you want to use the sound building and this building function. And then you can also plot the Beethoven's piece wave file, wave, to see what the Beethoven's shape, what's the Beethoven's shape. Okay, to see it. Okay, so in this case, in this Beethoven's piece, there are 8 notes. You can see 1, 2, 3, 4, 5, 6, 7, 8. There are 8 notes. So you can also use the built-in function frequency Z to find the energy distribution for each note, and you will find some complex. For example, let me see this. Yeah, let me see. I didn't check this. Okay, you can do this. I think you can try to. What you need to do is just extract every note and use the FREQZ to do the job. For example, X and X1, N, and FS. You can do this, and to analyze the loads frequency representation. Okay. So next one. Next one is you should analyze the circus piece. Actually, I think it's still we still do the same thing, just extract every note and show the frequency representation. I think it's easy to do. However, I think the most difficult part is to figure out how to extract every note from the circus. Since if you check the circus wave, you will find it's a very complex music piece. Let's show you. Okay. Yeah, I've counted the note number for this music piece, for this circus piece. It has around 45 to 47 notes. So I think if you extract every note manually, I mean by yourself, maybe it's a very well, maybe it's very boring to do this, but I think we can check the load pattern. I think for the circus note, or for the circus piece, you will find for each note, if we look into this note, it has a sudden rise and then a decay of amplitude. So I think this pattern is available for other notes. Of course, the pattern is similar, but they will have a different amplitude. Okay, and so I think every peak will be corresponding to every load. So I don't know. Maybe you can figure out whether oh, I mean, to extract the loads, I think you can find your way to do this. My way is not standard. So I think you can think about it and to figure out how to extract every load from this complex piece. So okay, and then you need to, after you extracting your loads, and what you need to do is just use the frequency Z to show the frequency representation. And I think that part is easy. And so the most difficult part is to extract the loads. Okay, okay. So I think I have covered the war materials about the lab 3. And since we will have 3 weeks, I think we have 3 weeks to finish the lab 3. So I think the time is enough. And yeah, hope Professor Zhou will cover the Fourier transform during our lab 3. So then you can have a good big picture for the Fourier transform. I think so. Yeah. Do you have questions? Yeah. Okay. If you don't have questions, you can stay here to finish your this tasks, or you can ask questions about the lab 2. Or if you have done lab 2, I think if you want to leave, you can just leave. Yeah. Okay. Thank you. Oh my God, no longer here. Oh my God, what's wrong? Mhm. One.